Swayam Prabha. Digital India. Educated India.
We will continue our discussions on central force motion. In the previous lecture, we had started off with Newton's law of gravitation, and we have solved the equation governing the motion of a particle in a central force, and we have looked at the solutions which are conic sections. In this lecture, we are going to move further in this direction. We are going to look at other kinds of trajectories. In the last lecture, we had looked at circular trajectories. Here, we are going to look at other forms of trajectories that are possible under a central force. And finally, we are going to discuss the energetics of a particle moving in a central force field. Just to recapitulate what we discussed, I started with this differential equation, which follows using Newton's second law and the gravitational law of Newton. We had found the general solution. We had fixed the phase by considering at theta equal to 0, r is equals to r min, obtained the solution in a very simple form. Here there is a correction. The tangential velocity is equals to the velocity, the speed of this particle at this point, cosine phi. Phi is this angle made by the velocity vector with e theta cap direction. We had expressed h, this is angular momentum per unit mass, which is r square theta dot, as r times v tangential. This follows from definition, and the tangential velocity is r theta dot. Then we looked at the conic sections and compared the solutions with the conic sections, and looked at circular path. So, this was all covered in the previous lecture. Today we are going to, in this lecture we are going to start with elliptic path. The solution of the kinetic equation, the equation of motion of the mass, is given, as well as the equation of the conic section is also specified, and the relation between these two equations. So, one comes from geometry, the conic section relation comes from geometry, the solution on the top comes from kinetics, and to have a match you must have this d in the conic section expression equal to 1 over c, which was the amplitude constant of integration, and eccentricity as c h square by g m, and the product E d is h square by g m. In an ellipse, as I have shown here, we start measuring, as we have set at theta equal to 0, r, the radial coordinate is r min, therefore, theta must be measured as shown here. Theta must be measured like this from this horizontal axis, and this is r min actually, this point is where the radial coordinate is minimum, I have marked it. Therefore, theta must be measured from that as the datum. Now, for an ellipse, the eccentricity lies between 0 and 1, and here what you will find is 1 over r can never be 0. Why? Because 1 over e is between 0 and 1, therefore, 1 over e is greater than 1. Now, cos theta, the value of cos theta varies from -1 to +1, it is bounded between these two. Therefore, this can never go to 1 over r can never go to 0. Therefore, these solutions for eccentricity between 0 and 1, they are bounded solutions, and this ellipse is that shape which you can find out, you can plot and see. Now, we define certain points. The perigee is the closest point on a particle which is moving around the earth in an elliptic path. Perigee is the shortest distance. Perihelion is the shortest distance for a particle which is moving around the sun. So, the shortest distance has this name perigee or perihelion, and therefore, it occurs at theta equal to 0. That is how we have defined it. Therefore, we can say R min, I will just put theta equal to 0 in our expressions and get R min. So, theta equal to 0, cos theta is 1, therefore, R min is 1 over c plus g m by h square, and this is from the kinetic side. From the geometry side, the conic section side, if you put theta equal to 0, it is E d by 1 plus E. E is the eccentricity, that is R min. Apogee is a farthest point on an elliptic path, around the earth as its focus, with earth as at the focus. Now, that turns out, if I put theta equal to pi, because theta is being measured from the apogee, from the perigee, at apogee theta equal to pi, that you can check. At apogee theta equal to pi, therefore, cos pi is minus 1, therefore, here I have R max is equals to 1 over minus c plus g m by h square. This is from the kinetic side. From the geometry side, conic section side, it is E d by 1 minus E. Therefore, the sum R min plus R max, and what is R min plus R max? If you look at the figure, R min plus R max is this full distance. A is the semi major axis, A is the semi major axis, B is the semi minor axis, half of the minor axis semi minor. So, A is this distance, therefore, this whole distance is 2A. R min plus R max therefore, is 2A, and from the geometry side it turns out to be 2 E d by 1 minus E square, 2 E d by 1 minus E square. This can be checked, and by by simplification of this relation, I can get the semi major axis in terms of the geometry. Eccentricity and d is the distance of the point from the directrix, that distance. Okay, so, distance of the focus from the directrix, that is d. Therefore, this semi major axis A is equal to E d by 1 minus E square, and from geometry, this is known from geometry that the semi minor axis is related to the semi major axis through the eccentricity E, like this. B is A under root 1 minus E square. This is a standard geometry relation. Now, if I look at 1 by R min plus 1 by R max, which I can find from whatever I have written in the left panel, you can look at this 1 by R min. So, it is C plus G m by h square, and R max is 1 by minus C plus G m by R square. So, 1 by R min plus 1 by R max is 2 times G m by h square. Right. So, 1 by R min plus 1 by R max is 2 times G m by h square, and therefore, I can also write this R min and R max as A into 1 minus E and R max as A into 1 plus E. So, these follow from all these steps that we have done. Just solve for, to get this, you solve for d from here, you find d, expression of d. So, d is A into 1 minus E square by E, and if you substitute d in here, you will get these two relations. and if you take the ratio r max minus r min by r max plus r min, that is E. These are all relations that I am showing you, which can be derived once you know the fundamental solution. These can all be derived, only this B is equals to A into 1 minus E square, that needs to be remembered, that is from geometry, and this comes from geometry. We continue with this elliptic path. Now, what I have done is I have removed all that clutter, and I have written down only the main relations. Let us move forward and see what we can derive from it. What we want to derive first is the orbital period. Now, orbital time period is area of the total orbit in the ecliptic plane. We have defined ecliptic plane. The area of the total orbit, now it is an elliptic orbit, area is known, and we have to find out A dot, the rate of change of this area, right, rate of change of this area. So, total area by areal rate will give us the time period of the orbit on the elliptic path. Now, this we have discussed before, this small area of this hatched almost triangle for d theta is an infinitesimal angle, is 1/2 r square d theta. Area of an ellipse is pi a b, comes from geometry, you can very easily derive it by integrating. Pi a b is the area of the ellipse divided by 1/2 r square theta dot. This comes from the areal rate dA dt. So, 1/2 r square theta dot, and therefore, it becomes pi a b, and r square theta dot, remember, is h, the angular momentum per unit mass represented by small h, lowercase h. So, pi a b by h by 2. So, that is the time period on the elliptic orbit. And if you use various relations, here I have used B is equals to A times under root 1 minus E square, I have used that in the first step, and then 1 minus E square I can write as E d by A. From here it follows 1 minus E square is E times d by A. And you know that E d from these two relations, E d is equal to h square by g m. E d is h square by g m. In the first step I have just written under root E d by A because it was under root 1 minus E square, and if I proceed further, if I do all these simplifications and use 1 minus E square as E d by A and E d as h square by g m, finally I will arrive at this expression of time period on the elliptic path. So, time period is the time required to complete one full period, one full rotation around the focus. Now, here you will notice if I do if I square this relation, I will get t square by A cube is 4 pi square by g m. On the right hand side everything is a constant. The central gravitating mass capital M is constant, g is definitely constant, 4 pi square, everything is constant. Therefore, t square is proportional to A cube. This was Kepler's third law. The square of the time period is equal to or is proportional to the cube of the radial distance. Here it turns out to be in elliptic path, it is A, the semi major axis, the length of the semi major axis A. So, in an elliptic path it is t square is proportional to A cube. For a circular path its t square is proportional to r cube, which we have already seen. So, this is Kepler's third law. Now, let us move to parabolic path. I have drawn this parabolic path again, theta starts from the datum where r is r min, Now, in a parabolic path the eccentricity is 1, eccentricity is 1, therefore, r can go 1 over r can go to 0, therefore, r can go to infinity, which means this is an unbounded solution. I mean there is a position where it can go unbounded. That means it will essentially escape, it will essentially escape from the central force field. So, this is a parabolic orbit and it will become unbounded at theta equal to pi. Why? Because at theta equal to pi cos theta is minus 1 and E is 1, therefore, it will 1 by r will become 0. So, r will go to infinity. Therefore, Gm by h square, E is 1. So, E is 1 because E is 1 here, therefore, Gm by h square is equal to C. And from here it follows that r is h square by Gm into 1 plus cos theta. Okay, so, that we obtain by eliminating C in the kinetic solution. What is r min? R min, we obtain r min when theta equal to 0. So, just put theta equal to 0 and that is r min, which is h square by 2 times G m. Next we have the hyperbolic path, which is obtained for E, the eccentricity greater than 1. Here 1 over r can go to 0 for certain values of theta which is less than pi and greater than minus pi, as shown in this diagram. The reason is E is now greater than 1, therefore, 1 over E is less than 1 and therefore, cosine theta will come to that negative of that value for some value of theta which is less than pi, right, and some, so but it will be in the second quadrant or in the third quadrant. So, you will have theta in the second quadrant for this to happen. Now, this is a hyperbola. Of course, this is an unbounded trajectory. Now, let us look again at this solution that we arrived at from the kinetics and from the geometry. So, once again I have written these two solutions. This figure, which is taken from the book of Merriam and Craig, this puts together all kinds of possibilities. For example, we had started with a circular solution for E equal to 0. This is that solution for E equal to 0, it is a circle. It maintains a constant radius with earth as the center. When you have E between 0 and 1, greater than 0, less than 1, then you have an elliptic orbit. This is the apogee, this is the perigee. The angle is measured from the datum here from the perigee, and this is twice the semi major axis. This is for epsilon less than 1. For parabola epsilon equal to 1, it is an unbounded orbit, hyperbola epsilon greater than 1 or E is greater than 1. So, that gives us the hyperbolic trajectory. The trajectories are therefore categorized by the eccentricity E. And once you have these two solutions in mind, you can do all possible derivations of various relations that we have shown. Now, we come to the energetics. This is the equation of motion. This we started off with mass times mass of the particle times acceleration is equal to the force. The force was because of the central force field minus G m by r square in the E r cap. So, minus comes because it is directed opposite to the ER direction, radial direction. We had the polar form of acceleration in the ecliptic plane. If you dot product the velocity, if you dot product the equation of motion with the velocity. So, suppose I dot product the equation of motion with velocity. Velocity is nothing in polar coordinates is nothing but r dot E r cap plus r theta dot E theta cap. If I dot product this with the equation of motion, then what do we have? In the ER we will get an r dot extra mass times r dot into this acceleration term plus E theta dot E theta cap dot E theta cap, again that is 1. There we have a contribution of r theta dot times this. So, r theta dot times this times mass, and on the right hand side we had r theta cap, and that gets dot with this term because E r cap dot E theta cap is 0. Therefore, you have only r theta r dot, you have only r dot on the right hand side as a product. This gives us a scalar, this gives us a scalar condition. I open up the bracket and simplify things, turns out to be this expression. I can recast whatever is in the bracket in this form, d dt, the total time derivative is half m r dot square plus half m r square theta dot square. This you will realize is the kinetic energy. These steps, I mean whatever we are doing now, discussing now, we have already discussed previously in case of particles. This is only we are applying those same steps in the case of a central force motion, a particle under central force. Therefore, d dt, so these were the steps followed in the work energy relation, if you remember. Therefore, this d dt of the kinetic energy is equal to the work done. Now, it so happens that the right hand side can be recast as d dt of g m m by r, g capital M times small m by r. And because of this I can take it to the other side. Now, you can, we have discussed all these things. The left hand side, as I mentioned, within the brackets is the kinetic energy of the particle, and the quantity within the brackets we have seen that this is minus of the gravitational potential energy of a mass in a gravitational field because of a central force field, right. So, this is the potential, right hand side bracketed quantity is the negative potential of a particle in a central force field, and left hand side bracketed quantity is the kinetic energy. Therefore, I can bring the right hand side to the left hand side and say that d dt of a certain quantity is equal to 0, which means that quantity cannot change in time, and that is the total energy, total mechanical energy of the system, and that happens to be a constant because d dt of this quantity is 0. So, this quantity itself must be constant, and that is the total mechanical energy. These things we have discussed in the work energy relations. Okay, so, this is the expression of the total mechanical energy, and you also recall that r square theta dot, which is angular momentum per unit mass, is also constant in the central force field. What I can do therefore is completely eliminate theta dot from the energy expression, and if I do that, I get that expression of energy, half m r dot square plus half m h square by r square minus g m m by r. H is a constant, angular momentum per unit mass, angular momentum is conserved. Now, I have written again our solution from the kinetics and from the geometry, and from here I know that E d is h square by g m, and all these things we have just now seen. R is at theta equal to 0, R must be equal to R min is equals to E d by 1 plus E. This comes from the geometry side. And therefore, if I eliminate that E d in the second expression using the first expression, then I have R min as h square by G m 1 plus E. Now, why am I doing this? Why do I want to find out R min? I want to find out R min because at R equal to R min, R dot is 0. At R equal to R min, R dot is 0. Substituting all these things in the expression of E at R equal to R min and R dot equal to 0, I can find out the energy at R min, and because this is constant, this is going to be the energy of the particle at any location. And if you simplify this, this turns out to be a very simple expression which is shown here, and from here I can calculate the eccentricity in terms of energy or energy in terms of eccentricity. Rest of the things you see are constant for a particle, right, small mass m and the angular momentum per unit mass. So, that you can set, and this relates the energy, eccentricity and the angular momentum per unit mass h, and we can calculate, express E in terms of the other quantities. Now, this is the expression of eccentricity. I will prepare a table and correspondingly I will write down the kind of trajectories we have. When it is a circle, E is 0, we know E is 0, and from that eccentricity expression I can find out what is E, capital E, the energy. Eccentricity small e, the lowercase e is 0 for a circle. Therefore, from the expression of eccentricity I can find out what is the energy for on a circular path, that is given on the third column, the first entry for a circular path. In the case of an ellipse, the eccentricity lowercase e lies between 0 and 1, and therefore, energy lies between a negative quantity and 0, it is less than 0, therefore, energy is negative. You should notice one thing, for a circular and elliptic path energy is negative, and also remember that circular and elliptic paths are bounded paths. Now, we come to parabolic path. In a parabolic path, E is equal to 1. If E is equal to 1, then from the expression of eccentricity we find that energy must be 0, and parabolic path is an unbounded orbit. It is not orbit, it is unbounded path, right, it is an unbounded trajectory. And for unbounded trajectory, therefore, for parabolic path E is 0. For a hyperbolic path E is greater than 1, and E, the energy, the eccentricity is greater than 1 and the energy is therefore greater than 0, it is positive. Therefore, by looking at this table we know that if the total mechanical energy of a particle in a central force field is negative, it is a bounded orbit. If it is 0 or positive, then it is an unbounded trajectory. So, this is our general expression of the energy. From here we can now calculate what is escape velocity. So, when will the particle escape? At least its energy, total energy must be 0. Therefore, if I put the total energy as 0, then I can get the escape velocity. Now, you should notice here that this term can be written as 1/2 m r dot square plus r square theta dot square, and r dot square plus r square theta dot square is nothing but v square. So, this is equal to this quantity is nothing but v square, the magnitude of velocity square. Therefore, this escape velocity, so this becomes half m v escape square minus g m m by r, this is the potential part, potential energy contribution. Now, this should be equal to 0, then the particle can escape. And if you solve for v escape, the escape velocity, it is under root 2 g m by r. You can look at the total energy expression in a different way also. Half of the kinetic energy contribution from the radial coordinate change and the rest of it you see is a function of r. Therefore, we can think about the rest of it as an effective potential. We can think about the rest of this term as an effective potential energy, V capital E I have written, the effective potential energy, which is only a function of r. And if you plot this function, it happens to be in with r, then it is of this shape. And I have marked out the different trajectories on this potential energy curve. When it is a circle, when the path is circular, it has only this. So, this is the energy, this is the level of effective potential energy. What happens in a circular path? In a circular path, r dot is 0, there is no change in radial coordinate. If there is no change in radial coordinate, this is the energy on a circular path, where r is to be replaced by the radius of the circular path. In a circular path, r dot, remember, is 0, therefore, the energy is only the effective potential energy with r replaced by the radius of the circle. And it has only one solution, and you can find out that by differentiating the. So, this is you see this is the minima, this is a minima point of the effective potential energy. Therefore, if you derivate the effective potential energy with respect to r and put it to 0, you will get the radius of the circular path, which is r c, as marked here. So, for a circle, just take the derivative, because the slope at this point is 0. So, d dr of V e is 0, and from here you can find out the radius of the circular path. So, if you simplify, you will get it, and you will also get the relation between the tangential velocity. So, the orbital speed and the radius, that relation you will obtain. Then, if it is an elliptic path, which is marked here, the r min and r max are shown here. At this level of effective potential energy, which is for the ellipse, wherever it cuts the effective potential energy curve, that those 2 points on the x axis will give you r min and r max. Therefore, for that level of energy in this potential well, the particle will move between these 2 radii, r min and r max, and this is effectively the elliptic motion which lies between some r min and some r max. So, the perigee and the apogee. If it is a parabola, you will notice that this curve becomes asymptotic with the r axis, the horizontal axis, it becomes asymptotic. Therefore, if the energy, effective potential energy, so the effective energy is 0, so then it is on the r axis. Therefore, the radial on one side it is bounded, there is an r min, but there is no r max. So, r max is infinity. So, it becomes unbounded. And here for a parabolic path E is 0. And finally, for a hyperbolic path which is for positive energy, for example, here of course it is unbounded on this in this direction, and this is r min. So, let me give you what we have discussed in this lecture. We have looked at the kinetic solution of a particle in a central force field. We have compared with the conic section solutions and studied various orbits, circular orbit and elliptic orbit, with these two are the bounded orbits. Then we discussed parabolic and hyperbolic orbits, which are unbounded orbits, and we have looked at the energetics of motion of a particle in a central force field. So, with that I will close this lecture.